Hey, Math 30-2s. Let's look at some exponential logarithmic functions today and how to interpret their graphs. All right. There are many applications of exponential logarithmic functions in real life. Recall that an exponential function is in the form y equals a times b to the x. A can't equal 0. B must be greater than 0, and x is any real number. We can use variations of this formula to solve problems involving population growth, growth of bacteria, radioactive decay, and other such growth and decay situations. When a is greater than 0 and b is greater than 1, we get exponential growth. When a is greater than 0 and b is between 0 and 1, we have exponential decay. All right. Logarithmic function with a base b has the equation y equals a times the log of x base b,
in the office, please. Brendan Garrick.
where x is greater than 0. We can never have the argument of a logarithmic function be negative, so that's that restriction. It can also be a real number, and b must be greater than 0 but not 1. So the base of the logarithm must be greater than 0 but not 1. So again, we're going to use variations of this formula to solve problems that involve magnitude of earthquakes, pH levels, sound levels, etc. So example 1. In 2012, the university population of a country was 160,000, was increasing at an annual rate of 4.5%. The growth in the university population can be represented by the exponential function p is equal to 160,000 times 1.045 to the exponent n. So there's our 100% of the population. Here's 4.5% of the population. If it's growth, we're going to have more than 1%, more than 100%. So that's why it's 1 plus 0.045 as our base of the exponential function. Note that it tells us p represents the university population, and n is the number of years since 2012. If the functions representing the population is a disguised version of this function, y equals a times b to the x, state the values of a and b. So a is 160,000, and b, the base of the exponent, is 1.045. All right. Use a graphing calculator to graph the function, which will show the population growth from 2012 to 2040, and state an appropriate window setting. So an appropriate window setting for x, well, x, we were told, is the number of years. We're going to use x for our exponent of n. So year 2012 could be year 0. Year 2040 is 28 years later. So maybe we'll go to a little bit more than 28 years. So maybe we'll go by 30, up to 30 years. And the scale we're going by, 1, 2, 5, 10, you know, that's all we're saying. So maybe let's go by a scale of 5. And our y window, which is our population, well, the minimum population this thing has, it starts off at 160,000. So, I mean, in 2012, that's what we have. So let's start with 160,000. Who knows how large the population is going to get? It might get to double that in 28 years. You would think. Hard to say, but you know, we're going to maybe say 4, 5, 600,000, something like that. And let's go by 100,000 as a scale. All right. So use the graphing calculator feature to figure out the following. So now let's go to our graphing calculator. Type in the equation that they gave us right here for y1 and use this window setting, and let's see if we get a graph. All right. So y1 is 160,000 times 1.045 to the exponent x. And that's great, but we need a window setting now. So we said our window setting was x. Number of years was from 0 to 30 by a scale of 5, I think we said. And our y minimum, well, we're starting at 160,000 people in year 2012. We're not sure how big it's going to get to, and I think we said 600,000 might be fine. And yeah, let's go by a scale of maybe 50 or 100,000. And that just tells us each tick on the y-axis. So now if I hit my graph, beautiful, there's our exponential growth. So the population is growing. If you look at your book, it says use the features of a graphing calculator to determine part C number 1, the population in the year 2015. Well, in this equation, P is equal to 160 times 1.045 exponent n. So in the year 2015, that means n is from 2012 to 2015, 3 years. So on our graphing calculator, n is represented by the variable x. So anytime I'm given an x value, I want to hit my trace function. Make sure we're on y1 and type in our x value of 3. So when x is 3, or in 3 years from 2012, our population is 182,586.58. So it doesn't tell us what it needs it to be, but that situation, we're not going to round that up. We're going to truncate off the 0.58 because we can't get to the next person at that point, right? So you're not going to increase that. So it's just 182,586. All right. So the population in 2015 should be 182,587. No, I say 586. Truncate that. There we go. Part 2, the number of years required to the nearest year for the population to double. For the population to double from its 2012 size, assuming that the growth rate continues to stay at that 4.5% annual rate. So now, in y2, y1 we've got our original function. In y2, I want to put my population that's doubling. So start at 160,000, double is 320,000. So type that equation into y2 and see what happens. So if I go y2 equals 320,000. 160. y2 is 320,000. All right. You hit graph. We'll notice our exponential growth function, the original one we were given, and here's the population y of 320,000. Now, you want to find the point of intersection. So you go second, calculate. Number 5 is the point of intersection. So you can scroll down and just hit the number 5. First curve is y1. Yep, that's highlighted as y1. Press enter. Second curve is y2. Yep, that's 320,000. Find the point of intersection of those two curves. I don't need to make a guess because there's only one point of intersection. So I'm just hitting enter 3 times. So it asks for the number of years required to the nearest year. So we've got 15.7 years here. If I look at 15 years, I wouldn't quite double. Here would be 15 years, so that's going to be below my 320,000. So I'm going to need to get to the 16th year before I at least double. So if that's year 15, I need to get to the 16th year. At 15.7 years, I'm right on 320,000. The nearest year, the next year that gets me at least double is 16 years. All right, so we will round this one up to 16 years. So y2 is 320,000. The year n should be 16 years from 2012. So x was 16. The year then should be 2012 plus 16. So 2028. All right. Example 2. The number of fish in a lake is decreasing by 5% every year as a result of overfishing. The number of fish present after t years is given by this formula. N after t years is NO times 0.95 to the exponent t. So it's decreasing by 5%. Notice the base of our exponent is less than 100%, less than 1. It's 100% minus 5%, or we're keeping 95% of the fish. We're losing 5. We're also told that NO is the initial population of the fish, and T represents the final population. What type of function is represented by the above formula? Well, this is an exponential function, but more specifically, Is this an exponential decay or an exponential growth function? Well, because we're losing 5%, this has to be exponential decay. All right. There were 2,500 fish present in June 2012. Write the equation of the function which would be entered into a graphing calculator to represent this scenario. So I'm going to let n at t equal y, and n at o, the original amount of fish, was 2,500. We've got our base of the exponent, 0.95, and our time is going to be represented by our x variable. Part 2, explain how to use a graphing calculator to determine how many fish you would expect to be present in June 2017. So to figure that out, we're going to let y1 equal this function, 2,500 times 0.95 to the exponent x. Put that into our graphing calculator. June 2017 is 5 years since June 2012, so we're going to let x equal 5 in our trace feature on the calculator. And we will look for the corresponding y value. All right, so let's do that and figure out what we get. So go to our graphing calculators, go to y equals, type in our new equation. The equation for the fish was 2,500 times 0.95 to the exponent x. And a window setting that makes sense. Doesn't give us one, so we must come up with one. Well, x is the number of years from June 2012. So start at 0 and go 30 years. Well, we just want to find 2017, which is 5 years. So maybe we don't have to go to 30. Maybe let's just go to 15 by a scale of 5 is fine. And our y minimum, well, we can get all the way down to 0 fish, and we're starting at 2,500 fish. So we're decreasing from 2,500 down to 0. Let's make our scale maybe 100. And there we go, our exponential decay. So we said in our notes, if I'm looking to find how many fish are in 2017, you hit your trace function, and you type in a value for x of 5 years. Right? 5 years from 2012 was 2017. So there's 1,934 fish. All right. So 1,934 fish in June of 2017. Part C asks the question, how many years to the nearest tenth would it take for the fish population to reduce to half the number as there were in June of 2012? So now in Y2, I'm going to type in half the number of 2,500, so 1,250. And I'm going to find the point of intersection. Point of intersection of Y1 and Y2. So we already have Y1 in our calculator. Let's go to it and type in Y2. In Y2, I'm going to take half of 2,500, 1,250. Press graph, and we can see that it just barely fits in our viewing window. Had the intersection point not shown up in our viewing window, we would have had to expand our viewing window to make sure we saw that point of intersection. But because it's there, we just have to go second function, calculate, number 5, the point of intersection. I've only got 2 curves, so I just have to press enter 3 times, and there's only 1 point of intersection, and there it is, after 13.5 years. So it asks to the nearest tenth of a year, so we're going to say after 13.5 years. there is 12,500 fish. Sorry, 1,250 fish. Good. Let's look at example 3. Let's read through this question. In chemistry, the pH of a solution is defined as pH equals the negative log of H positive, where the H positive is the hydrogen ion concentration expressed in moles per liter. On the grid, sketch the graph of pH on the y-axis, there it is, and the hydrogen ion concentration, H positive, on the x-axis. Use the window provided, x and y. So let's graph that in our graphing calculator, then sketch it in our notes. So go to y equals, clear these equations, and in y1, let's type in the equation we had. Negative common log of H positive, that's going to be my x value. So the negative common log of H positive, and I want to change my window setting, otherwise this won't match up. So in our notes, x minimum is 10 to the exponent negative 6. X max is 10 to the exponent negative 3. The x scale is 1. Y goes from 3 to 7 by a scale of 1. Now if we hit graph, we should see our exponential function. Sorry, our logarithmic function. So let's redraw that in our notes. So that graph should look something like this. Right? Y goes from 3 to 7. All right, and this goes from 10 to the negative 6 to 10 to the negative 3 on the x-axis. Determine the pH of a solution to the nearest tenth if the hydrogen ion concentration is 3.4 times 10 to the negative 4 moles per liter. So that means on our calculator, we want to type in x as 3.4 times 10 to the negative 4 on our trace function and find the corresponding y value. So let's do that. So in your trace function, type in x is 3.4 times 10 to the exponent negative 4. And that corresponds to this point on the graph, which is 3.4685211. So a pH level of about 3.468. It says the nearest tenth, so a pH level of 3.5. So y equals 3.468 and so on. We want a pH level then to the nearest tenth of 3.5. All right. Part C, a patient gave a urine sample which was found to have a pH of 5.7. What was the hydrogen ion concentration? So now if I'm given a pH level of 5.7, that translates to Y2 in my graphing calculator as 5.7. And then I want to find the point of intersection between Y1 and Y2. Y1 and Y2. And that's going to be the solution for the hydrogen ion concentration. So go back to Y equals, go down to Y2, type in a pH level of 5.7, graph it, and we see the point of intersection is right here. So second, calculate that point of intersection, number 5. Y1, yep, Y2 is 5.7, make a guess, don't have to, there's only one point of intersection, and there it is. 1.9953 times 10 to the negative 6. So x equals 1.9953 and so on times 10 to the negative 6. It wants this answer in scientific notation to 1 decimal. So my H positive hydrogen ion concentration would be 2.0 times 10 to the negative 6 moles per liter. Perfect. Example 4 talks about carbon dating. So the decay of radioactive elements can sometimes be used to date events from the Earth's past. In a living organism, the ratio of radioactive carbon, which is carbon-14, compared to ordinary carbon remains fairly constant. However, when the organism dies, no new carbon is ingested, and the proportion of carbon-14 decreases as it decays. An estimate of the age, X years, of organic remains can be determined from the exponential function. P equals 1,000 times 1/2 of x divided by 5730 as the exponent. And we're told P is the percentage of carbon-14 remaining. All right. State a suitable domain and range for this exponential function. So domain, I might say that my x variable is the number of years. So we don't want to have any negative years. Let's just say x is greater than or equal to 0 for our domain. And our range, which is our p-value, percentage, well, p must be greater than or equal to 0%, but less than or equal to 100%. All right. We can't have less than 0% or more than 100% of carbon-14 remaining. Graph the function using a graphing calculator with this window setting. So let's do that. So in our graphing calculator, let's clear what we had in here. And let's type our new equation. P or y equals 100 times 0.5 to the exponent in brackets x divided by 5,730. Enter. Window setting to make this graph appear. We're told in our notes that x should have a minimum of 0, a maximum of 20,000, and go by a scale of 10,000. Y should have a minimum of 0%, maximum of 100%, not 1,000, 100%, and go by a scale of 50. Now if we graph it, we see our exponential function. This is decay because the base of our equation is a half. Base of our exponential function is a half. Now let's read what it wants us to do. On May 1, 2012, a family in Whitehorse was digging up their basement when they discovered what were believed to be the remains of a prehistoric bison. An online article the same day in the Globe and Mail indicated that paleontologists thought that the bones might be about 10,000 years old, but that carbon dating results were required for verification. If the skeleton of the bison is about 10,000 years old, what percentage to the nearest whole number of carbon-14 should the paleontologists expect to find in the bones? So we've graphed the function y equals 100 times a half to the exponent x over 5730. That's y1. How do I find the amount of carbon-14? Well, we're told a year. That's our x. We're told the bison is 10,000 years old. So in our trace feature, type in x is 10,000 and find the corresponding y value. That's all there is to it. So go back to your calculator, hit trace, type in an x value of 10,000. Well, I mean, it just happened to show up, but at 10,000, we've got a y value of 29.829. So y is 29.829, and so on. And it wants the percentage to the nearest whole number. So we're going to say there is 30% carbon-14 remaining. Part D, a bone fragment with the carved image of a mammoth was discovered in the southern U.S. state of Florida in June 2011. If the carbon dating test indicated that approximately 20.3% of carbon-14 was left, estimate the age of the bone fragment to the nearest 1,000 years. So now I want to go into my Y2 equation and type in 20.3% and then find the point of intersection between Y1 and Y2. And that point of intersection, we're looking for X. So in Y2, I want to type in a percentage of 20.3, and when I graph that, it should intersect my exponential function. I want to find the point of intersection, so second calculate the point of intersection, and we just have to hit enter 3 times. And there we go. X is 13181.569. So X is 13181.569 and so on. It wants it to the nearest 1,000 years. So nearest 1,000 years looks like about 13,000 years old. All right, great. You guys have your assignment. Where you go.